Hello friends, welcome to PG department of LJ University. This is a lecture series of applied mathematics for the first semester student in computer engineering branch. Here I, Dharmin Patel, presenting a lecture on the topic diagonalization of any square matrix. So in the previous lectures of eigenvalue and eigenvector, we studied about how to find the eigenvalue and eigenvector for 2x2 matrices, 3x3 matrices, and now we will discuss on diagonalization of matrices. So in this lecture we will cover the contents from unit number 1 linear algebra is diagonalization of a square matrix, examples of diagonalization of square matrix and Cayley-Hamilton theorem for eigenvalue and eigenvectors. Now we will start with the diagonalization of square matrix. Here A is a square matrix of order 3 cross 3 and lambda 1, lambda 2, lambda 3 are eigenvalues for matrix A. So already we know about how to find the eigenvalues and eigenvectors. So here our first step is how to find the eigenvalues and eigenvectors for a given matrix. It is either 3 cross 3 or 2 cross 2 order. Here eigenvector corresponding to lambda 1 is x1 y1 z1. Corresponding eigenvector for lambda 2 is x2 y2 z2 and x3 y3 z3 is a eigenvector corresponding to lambda 3. So now we make a one matrix. Here our matrix is look like x1 y1 z1, x2 y2 z2 and x3 y3 z3. Here remember that here we have to maintain the order of eigenvector. It is necessary for the diagonalization of square matrix. We can interchange the order of eigenvectors, but remember at the multiplication level. Here we write down the first eigenvector u1 in the first column, second eigenvector u2 in the second column, and third eigenvector in third column. Then after we will find the inverse of this eigenvector matrix. It's sometimes known as model matrix. Here we have a eigenvector matrix or model matrix is like this: x1 y1 z1 first column, x2 y2 z2 second column, x3 y3 z3 third column. Now we will find the inverse of this eigenvector matrix. It is always exists because these eigenvectors are always linearly independent. In this case, determinant of P is every time not equal to 0. So using the formula of this matrix, inverse of matrix P is P inverse equal to 1 upon determinant of P into adjoint of P. Already we know the how to find the determinant of P and adjoint of P. So I recall here how to find the adjoint of P. So here adjoint of P is nothing but cofactor matrix of each entry of given matrix 3 cross 3 or 2 cross 2. So it's a cofactor of every element, and then take the transpose of that cofactor matrix, which is our adjoint of P. Here suppose we are taking the cofactor of x1, so it will be y2 y3 z2 z3 subdeterminant, and calculate it. Here x1 is in the first column and first row, so it is a positive. If we are taking the cofactor of x2, it is in the second column and first row, so it's a negative entry. Its cofactor value is negative entry, and after that in x3 we have again positive entry. So we already know the how to find the adjoint of matrix P. So according to that, first of all find the P inverse. Here after finding the P inverse, we multiply P inverse. Suppose we have a P inverse is K1, K2, K3 in the first row, L1, L2, L3 in the second row, and M1, M2, M3 is in third row. So here remember that we are taking the in the P inverse, we are taking the transpose of cofactor matrix. First of all, find the cofactor of each entry, then take the transpose with the sign, and here our already we know here P is x1, y1, z1, x2, y2, z2, x3, y3, z3, which is our eigenvector matrix. Now, to convert our original matrix A into the diagonalization form, we are taking the transformation P inverse AP, and after multiplying this 3 cross 3 matrices, we have some diagonal matrix P inverse AP equal to lambda 1 in the first column, first row, lambda 2 in the second column, second row, and lambda 3 and lambda 3 in the third row, third column. Here, remember that we are taking the u1 in the first column, so our first entry in the first row is lambda 1. If we interchange the order of the eigenvectors, so at the last stage, after multiplying P inverse AP, we have a order of the eigenvalues in the diagonalization process may be changed. So that is the concept of diagonalization of 3 cross 3 matrix, and it is always similar for every square n cross n matrix. Now we will see some examples of diagonalization. So here, diagonalize this matrix. So already in the previous lecture we studied about the eigenvalue and eigenvector for this particular example. So here I am writing the eigenvalues and eigenvectors for this particular matrix directly according to the previous lecture. So first we will find the eigenvalues and eigenvectors for this particular matrix. So here we already found out in the previous lecture, so I am writing here directly. So here eigenvalue is 1 and its corresponding eigenvector is -1, 0, 1. For -1 we have 1, 2 and 1, and for lambda 3 equal to 2 we have eigenvector 1, -1 and 1. You can easily see that all the eigenvectors are linearly independent. Now we will make the one model matrix or eigenvector matrix. Here we write down the first eigenvector in the first column, second eigenvector in the second column, and third eigenvector in the third column. Here we can interchange the eigenvectors columns, but remember that at the end of multiplication of P inverse AP, we have a order of eigenvalues is depends on this model matrix. So now we will find the eigenvector matrix. Here we already found out it, and now we take the inverse of this particular matrix. So I am writing the inverse of that particular matrix directly, and now we have a P inverse AP is look like this type of matrix, and now after that we have a corresponding diagonal matrix is -1. Now we have a corresponding diagonal matrix is 1, -1 and 2. That is our diagonalization process. Now we will see the new topic of eigenvalue and eigenvector, which is the Cayley-Hamilton theorem. So it is depends on the characteristic equation of the matrix. So what is the statement of Cayley-Hamilton theorem? Remember, it is very easy. Every square matrix satisfies its characteristic equation. That is a very simple concept of Cayley-Hamilton theorem. Now we will understand it properly. Here A is a 3 cross 3 matrix, and its characteristic equation is lambda cube minus s1 lambda square plus s2 lambda minus s3 equal to 0. And what is the concept of Cayley-Hamilton theorem? So here we replace lambda by our original matrix A. That means our equation becomes a cube minus s1 lambda square plus s2 lambda A. Suppose this is our characteristic equation and we replace lambda by A in the characteristic equation. That means a cube minus s1 a square plus s2a minus S3I. Here I is 3 cross 3 identity matrix. So right hand side will be 0 matrix. So that is the concept of Cayley-Hamilton theorem. If our matrix is 2 cross 2 matrix, so in this case we replace our lambda by 2 cross 2 matrix A, and again we get the right hand side value is 0 matrix. In this case, the last step is identity matrix of order 2 cross 2. So here S1 is trace of matrix A, S2 is sum of minus of diagonal entries, and S3 is determinant of A. So for 2 cross 2 matrix, we can similarly apply it like this. A is a 2 cross 2 matrix, so its characteristic equation is lambda square minus S1 lambda plus S2 equal to 0. Here A, we replace lambda by A. In this case, A square plus S1A plus S2I equal to 0. That is the concept of Cayley-Hamilton theorem. And after that, here S1 is a trace of A and S2 is determinant of A. And now we will see some examples related to Cayley-Hamilton theorem. Here we have a 2 cross 2 matrix and we have to verify it with the Cayley-Hamilton theorem. So here, first of all, we will find the characteristic equation of this 2 cross 2 matrix, which is lambda square minus S1 lambda plus S2 equal to 0. So it's S1 equal to trace of A, which is 4, and S2 is determinant of A, which is 1. We can easily verify it. And now our A square minus S1A plus S2I equal to what? That is our Cayley-Hamilton theorem. So if we get the 0, then our Cayley-Hamilton theorem is verified. So here A square means it's a square of 1, 2, 1, 3 square. S1 is 4, and S2 is determinant of A, which is 1. So here we replace the lambda by A, and now after simplifying this particular matrix, we get the 0, 0, 0 on right hand side. That is the verification of Cayley-Hamilton theorem. You can easily verify. Here I am not calculating the multiplication A square and this summation of particular matrices. You can easily verify it. So here already we discussed about the diagonalization of square matrix, examples of diagonalization, Cayley-Hamilton theorem, etc. And now in the next lecture we will discuss the concept of linear transformation and its examples from the unit number 2 of linear algebra. Thank you very much.